In this video, we will discuss all the differentiation rules we have learned so far. And after that, we will see a few more examples and also another very important differentiation formula. Okay, so let's start from the functions. We know how to differentiate, right? So if you have a constant c, c prime, we know that's 0. And the power function, if you have x to a prime, so this is a times e to, no, a times x to a minus 1. Exponential functions, e to x prime is e to x. And now we go to trig functions. Sine of x prime is cosine of x, and the cosine of x prime is negative sine of x. And the last one we have so far is tangent of x is prime is secant square of x, right? So that's basically how the collection of elementary functions we know how to differentiate. Now we also have other rules, right? If you can generate new functions by taking a sum, difference, multiply a number or product or quotient or compositions. So that's the other rules we have. So we suppose we have two functions and f g here are a differentiable function. Differentiable functions, which means f prime and g prime exist, right? And also related properties are satisfied when we talk about compositions. So first one here, you can get a new function by taking a multiplication with a number. So let's see the c dot f prime is c dot f prime. Right? You get new function by multiplying by a number. All you need to do when you try to differentiate this new function, all you need to do is differentiate that function, then time that number in the end, right? Then you have f plus g prime is f prime plus g prime. Similarly, f minus g prime is f prime minus g prime, right? So that is three rules we have. And what's next is we can try to differentiate product, right? And we have that f dot g prime is f prime dot g plus f dot g prime. So that's product rule. And also we can differentiate reciprocals. 1 over g prime is negative g prime over g squared. And then we get our quotient rule, which is f over g prime is f prime dot g minus f dot g prime over g squared. And we have one more rule so far, which is the chain rule, right? We can get a function by taking compositions g of f of x, right? You need, given a big function, you need to figure out what is the inner function, what is the outer function. In this case, inner function is g of f, outer function is g. We want to differentiate this function here. This is g prime of f of x, then times f prime of x, right? So we can try to extend, apply chain rule. So the last one here is called chain rule to some specific outer functions. For example, if you want to differentiate g of x to the power a here, prime, right? So in this case, that is a what's that called? Is a composition of two functions. Outer function is the power function, right? And so this is equal to apply the power rule, bring a down, and keep the inner function g of x, then minus one on the minus one, a minus one there to the power x, a minus one, then times g prime of x. And what if the outer function is the exponential function e to g of x prime? So this will be e to g of x because exponential function, the derivative doesn't change, right? Then times the derivative of inner function g prime of x, right? One more formula here is psi of g of x prime. So this is cosine of inner function g of x times g prime of x. So that's all the rules we have discussed so far, right? So this is basically the rules we can apply to differentiate a function in the explicit form, right? Y equal to a formula of x. We can differentiate that function using all the rules we have so far. Now let's see another example, right? Let's see more examples. Example. Let's see the exponential function y equal to a to x, right? We do know that here for sure we assume a here greater than 0. And we do know that if a is e, then derivative is e to x. What about other base, right? 2 or 5. So let's see this, right? Recall that we know that a here is e to the power natural log of a. Let's try to make a connection between with our number e here because we do know how to differentiate the exponential function e to x. So this function, we know that a to x is basically e to the power natural log of a, then to the power x, right? Then apply the exponential rule, we get this equal to e to the power natural log of x dot with x, right? Now let's try to differentiate a to x. So a to x prime is e to natural log of a times x prime. This is a composition of two functions. We can apply our formula here, right? With g of x equal to natural log of a times x, right? We do know that natural log of a times x prime is natural log of a is a constant, x prime is 1, so this is natural log of a, right? So this is equal to e to natural log of a dot x times natural log of a, right? And we know that e to the power natural log of a dot x is a to x. So this is basically a to x times natural log of a. So we get our general formula for the general exponential function, right? So we get our one more way formula here is a to x prime. So in general, this equal to a to x times natural log of a, right? This agree with the formula we have for e to x because natural log of e is 1, right? So this is another formula we should know. Put it into our collection, right? So, okay, now let's try to handle some complicated functions. As the example 2 here, we have y equal to square root 2 minus e to x over tangent of 2x. I can see that, look at our function. We want to apply the rules we have so far to differentiate this function here, right? What rule do we apply? Look at this function. You see a quotient. So we can apply quotient rule first. So we can see that by looking at this formula here, so we want to apply quotient rule first. We need to use quotient rule. Let's try to apply quotient rule, right? So this equal or y prime is square root 2 minus e to x prime times tangent 2x minus square root 2 minus e to x times tangent 2x prime over the denominator square, right? 2x to the power 2. Now you need to differentiate the numerator, which is root 2 minus e to x, and denominator, which is tangent 2x. Let's put that here, right? Square root 2 minus e to x prime, right? I can see that this is a composition of two functions. So this is 2 minus e to x to the power 1/2 prime. So that's a inner function is 2 minus e to x. Outer function is 1/2, right? You can write this as f, okay, g to be x to 1/2. F is 2 minus e to x. And so g of f will be this function here, right? And so you can see that if you have g of x is x to 1/2, f of x is 2 minus e to x, then g of f of x is uh, is 2 minus e to x to the power 1/2, right? So now we can apply chain rule, right? Our second rule we want to apply is chain rule for sure. We do have to use the derivative of e to x and also difference of two functions, right? So this is equal to, right? This equal to, we know how to differentiate outer function, which is 1/2 2 minus e to x to the power 1/2 minus 1, which is negative 1/2, times the derivative of f, right? F, you can apply a difference rule. Difference rule on 2 minus e to x, right? 2 prime is 0, e to x prime is e to x, so you get negative e to x, right? And now let's try to differentiate tangent of 2x prime. So that's a clearly composition of two functions. Inner function is 2x, outer function is tangent. Apply the chain rule. Duality of tangent is secant square, right? Inner function 2x keep inside, time 2x prime, you get 2, right? So we are now ready to write down the final answer. The final answer is 1/2 2 minus e to x to the power negative 1/2 times negative e to x, then times tangent of 2x minus 2 minus e to x to the power 1/2 times secant square of 2x times 2 over tangent of 2x square. So that's how do we differentiate this big function, which is obtained by taking a quotient and also a couple chain, right, compositions. Now let's see a few more examples, right, on how to differentiate functions. Let's see B here, second one here, right, a third one. And third one here, the function is also kind of big, right? Y equal to sine of sine of sine of x, right? You can see that this function here is obtained through taking the composition 2 times, right? So that's how do we get this function. And inner function here, you take another sign, you take another sign, right? So we can apply a chain rule, right? Starting from outside, keep the inner function, and then differentiate inside, right? So apply chain rule twice, basically, right? This is the only rule we will use is chain rule and also the derivative of sine function, right? So starting from the most outside, sine, you get this is sine prime is cosine, keep the inner function, sine of x, and times the inner function sine of x prime, right? Now the second factor here, still a composition of two functions. Apply chain rule one more time. You get cosine sine of x times cosine sine of x, then times the derivative of the actual inner function, which is cosine of x. So this is how do we apply chain rule to differentiate the composition of multiple functions, right? Okay. So that's our third example. Now let's go to fourth. And the fourth one is f of t equal to 4 to the power t times sine of t cube. So that's a complicated composition, product composition kind of function, right? So let's try to apply the rules we have. Clearly, you need to use chain rule and also you need to use a product rule, right? And so f prime of t. So what's the outer function? The outer function is fall to something, right? Fall to a function of t, right? So we can apply the formula for differentiating exponential function whose base is 4, right? We know a to x prime is a to x times natural log of 4. So the outer function, the derivative should be 4 to the nothing changes, 4 to t times sine of t cubed and times natural log of 4. Then time the derivative of the inner function t times sine t cubed prime. Now here we have a product of two factors. I try to apply product, right? So this is 4 to the power t times sine t cubed times natural log of 4 times product t prime, you get 1. You get 1 times sine of t cubed plus t times the derivative of this function here, right? The derivative of that function, clearly you need to use chain rule. Outer function is cosine, sine, so derivative is cosine, right? Cosine of the inner function t cubed times the derivative of the inner function, which is t cubed, which is power root t 3t squared, then close it. So that is the derivative of this function, right? So here we used, let's try to list the rules we have used. We used chain rule twice, and also we use product rule. Product rule. Okay. Let's see our example number 5. Example number 5. The function is given by h of x equal to x squared minus 1 over x squared plus 1 to the power 6, right? So you can see that, look at this function, you see a power function in first to the power 6, inner function is the quotient. So clearly, you can write down the rules we have to use. We have to use a chain rule and quotient rule, right? We will try to differentiate the inner function. You do have to use quotient rule, right? So let's try to write down the answer here directly, because after all the examples, we should feel better ready to differentiate a function directly, right? So h prime of x, let's try to discuss the procedure here. Outer function is x to the power 6, power rule, bring 6 down. X squared minus 1, inner function still, x squared plus 1 to the power 5, then times the derivative of the quotient, right? We apply quotient rule. This is x squared plus 1 square, the quotient square. Numerator prime, which is 2x, x squared plus 1 minus x squared minus 1 times the derivative of the denominator, which is 2x. So this is how do we differentiate this function here, right, as the derivative of this big function, right? Now, after this video, right, I hope you have a good understanding of all the rules we have learned so far, and also how to use them to how to apply them uh, to differentiate, to find the derivative of some very big functions.